Let's just kind of go through the things we've talked about with sigma notation. First of all, if you take your time and draw it slow, it sort of looks like that. It is the capital letter sigma in the Greek alphabet. It is also known as summation notation, and that's because it represents a series. And the top and bottom numbers are just the numbers that we enter, and they're always integers. You can start with, you can use any letter, I. I is a popular one. I'm not sure why it is, but it's a popular one when you get into calculus. A lot of times they'll use sigma notation with I. I find it personally a little confusing, but only because I think imaginary numbers when I think I, but it's not my place to decide, right? And then this will always give me a start value, the first number I plug in, and I'm just going to put a 3 there. That's the first number plugged in. And then we'll do on the top the last number plugged in. And remember, we go through every integer in between. So I plug in 3, I plug in 4. Even though 4 is not listed, it comes between 3 and 5, and I stop at 5. And then I'm given some directions. I'm going to make them real easy right now. I'm going to say 4i. Just for ease of what we're doing. If I plug the values in, it would be 4 times 3 plus 4 times 4 plus 4 times 5, or 12 plus 16 plus 20. This here is known as expanded form. Again, if it ever says expand, that's what they're looking for. You could have the first part alone, you could have the second part alone, or you could have both parts when it asks you to expand. It doesn't matter. Those are the pieces of expanded form. When I actually add them up and get a value, so this is 48, that's what they're looking for when they say evaluate. And like I said yesterday, summation notation or sigma notation can be used and is used even in programming of your calculators to take big kind of incomprehensible situations and to compact them into just a series notation. And again, that's how they program sine and cosine and tangent into your calculator, because there's no real direction about how that ratio works. So what they did is they came up with a polynomial that they could write in using sigma notation and summation notation, and then your calculator just kind of goes through the process and does those. Remember, we fell into that little bit of a problem when we were trying to use our calculator to solve, where it would only give us one answer even though there were multiple. And that's, again, because it's programmed only in that one way. And through sigma notation, we are able to use our calculator to calculate it, as opposed to the olden days when they just had to look everything up in tables. Okay? So we're going to practice writing using sigma notation, and we already kind of started that yesterday, but I'm going to kind of push you to look for some different things or other things that might happen. So first of all, the very, very first thing that you want to do when you are trying to write using sigma notation is you want to check to see if it is a pattern or a sequence that we know. Is 3, 6, 9, 12, blah, 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 up to 60 a pattern that I recognize? It is. It's actually an arithmetic sequence. And even though it's not limited to this, plus 3, plus 3, plus 3, plus 3, even though it's not limited to what I'm going to do, we usually write it this way because it is a quick, foolproof way that will work every time I have an arithmetic sequence. And that is, I use a sub n equals dn plus a sub 0. I just use that form, that explicit form, and I plug it in that way. So my sigma notation looks like, here's my lazy way of sigma notation. My sigma notation looks like what this is 3n plus 0. Because remember, if I go back to a sub 0, it would be 3 before that. Or just 3n. I will put that there. So arithmetic, just use your explicit formula. Again, it's not limited to that, but it's a safe, foolproof way. Because I'm using explicit formula, because I'm treating this like it is a sequence, I can just count the term numbers. I am trying to generate the first term, the second term, the third term, the fourth term, and blah, 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 all the way up to this, whatever gives me 60. And so I might need to figure out where I stop. And to do that, it's pretty easy. If I were to generate this, what number would land at 60? And so that's where I'm going to stop on this. And would be 20, so my last one is. Even though they don't have them all listed in there, that is my real quick basic form of sigma notation. So arithmetic, great, I have it. Quick, easy way to write it. Again, you can write this a different way. I could write this as sigma notation, 3n plus 3, start at 0 and end at 19. Because if I plug in 0, 3 times 0 plus 3 is 3. If I plug in 1, 3 times 1 plus 3 is 6. If I plug in 19, 3 times 19 plus 3 is 60. But why write a million different ways? Again, just kind of stick with what is going to work every time. Okay, that's my recommendation. If you want to be spicy, go ahead and be spicy. But this is the one I will typically use, all right? If it's not arithmetic, then I want to check it out and I want to see if it's maybe geometric, because I have a nice formula for that. So is 48, 12, 3, 3/4, ... forever and ever, is that arithmetic? No. Is it geometric? Yes. Remember, in geometric, you do not divide, you always multiply, and so if it's getting smaller and smaller and smaller, you're multiplying by a fraction. My r can be found by taking 12 over 48, which should be the same as 3 over 12, which should be the same as blah, 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 and actually it's 1/4. So because I am using the explicit form for a geometric sequence, which is a sub n equals a sub 1 times r raised to the n minus 1 power. Because I'm using that, I'm going to start my sequence at 1 because I want to generate the first term, and then I want to generate the second term, and the third term, and the fourth term. I'm treating it like it's a sequence. And so when I put it in my formula, 48 times 1/4 to the n minus 1 power, I just need to go ahead and figure out what that top number is. And what does ... indicate to me? Goes on and on and on forever. And so we have a symbol for that as well in math. We have symbols for everything. That means I'm not stopping, I'm going to infinity. And so this would be my easy, quick answer. So arithmetic, geometric, just pull out the explicit formula and treat it like it's a sequence. You can count the number of terms, or do some algebra if necessary to find the term numbers, or again, it can go to infinity here. But keep in mind, I could write this one a different way as well. I could maybe start it at 0. Still, I'm going to go to infinity because infinity is forever. And maybe I would do 48 times 1/4 to the n power. It's going to generate the same sequence, but for what we're doing, if we just stick with our explicit, we'll start at 1 all the time and keep count our terms and work that way. That was kind of why I wanted to show you that sigma notation on the bottom of the sheet and try and get you to realize that two different looking things can generate the same sequence. All right? So arithmetic, yay. Geometric, yay. Not always arithmetic and geometric. And we talked about this a little bit yesterday as well. Sometimes it's going to be something else. And a very common something else is perfect squares or perfect cubes. Another common one in calculus is factorials. How many of you have ever worked with factorials yet? If you did AP Stats, you probably did. If you do some programming, you probably work with factorials. When you get into Calc, you'll for sure see some factorials. So let's do a definition of a factorial. If I want to find in the most basic form, if I want to find something like 4 factorial, that's my symbol for factorial. It's an exclamation mark. All of your calculators have a factorial. Usually on the fancier calculators, you'll find it under probability, which is PRB on some of them. Some of them are just symbols. On this one here, I go to PRB, and then it gives me the very last, oops, can't see that? The very last one is the exclamation, all right? And on mine, it's, again, PRB right here under the degrees radians. Some of you might have to go into mode or menu, again, depending on how fancy your calculator is. But what factorial means is I am going to take this number and I'm going to multiply it by every integer underneath it down to 1. And so 4 factorial is 4 times 3 times 2 times 1, which is 24. 5 factorial is 5 times 4 times 3 times 2 times 1, or 24 times 5, 120. Get the gist? Not that you need to know how to do those right now, but I just wanted to show you what they look like. And so both of these are examples of special instances or different patterns that we have out there. This one is clearly perfect squares. You guys recognize that, yes? Yeah. This one here is factorials. And so if you find a pattern, you can just write it in its own unique form. If it's perfect squares, I'm just going to square each number. So when I do my sigma notation, the first number I'm going to square is 1. The last number I'm going to square is 6. And I'm going to square it, so that's my direction. That's all I'm doing there. That's my formula. Here are factorials. And I should have pluses between these if I want to write it as a sum or a series. And so this would start at 1 and end at infinity, and this is n factorial. And again, just to kind of take a look at that, if I expand this out, this equals 1 factorial, which is 1, plus 2 factorial, which is 2 times 1, this is just 1, plus 3 factorial, which is 3 times 2 times 1, which is 6, plus da-da-da-da. You get the gist, right? Good. Okay. So special cases are out there. You might have to look for them. Remember also that sometimes, especially when it's not arithmetic and not geometric, it doesn't necessarily have to start at a nice starting point. So you could get something like, here's just a side example. I'm going to do 27 plus 64 plus 125. I'll stop there. Let's do that one. What's the pattern? Perfect cubes. Pulled them right off the perfect cube list there. So when I make my sigma notation, I'm going to cube whatever value I plug in. But even though all of the other ones have started at 1, I don't want this one to start at 1. Because cubing 1 isn't going to get me 27. I need to make sure that the first number I plug in generates 27. So that makes me start at 3. And then 4 cubed is 64. 5 cubed is 125. So first, check if it's arithmetic. Second, check if it's geometric. Third, check if it's a special pattern. Is it perfect squares? Is it perfect cubes? Does it look like it might be factorials? But we're still not limited to those. And in fact, sometimes we're even going to get things that are like messy and hard to see a pattern in them. And we have to kind of adjust it and see if we can make it look like a pattern. And so in a problem like this one, I might start by trying to get all of these with a common denominator. I might start that. So if I do, I get 4/10, because I multiplied the top and the bottom by 2, plus 5/10 plus 6/10 plus 7/10 plus 8/10, I am seeing a pattern. So it didn't look like a pattern at first. It didn't have perfect squares, perfect cubes. I didn't see anything there that made sense, but now I do. I can approach this once I find my pattern a couple different ways. This is arithmetic, right? What am I adding each time? 1/10. So I could do this starting at 1, ending at 1, 2, 3, 4, 5, and then putting it in my dn plus a sub 0. So in this case, it would be a sub 0 is 3/10, d is 1/10. So this would be 1/10 n plus 3/10. Could totally do it like that. It is arithmetic. It wasn't obvious, but once we figured it out, it was. I could approach it another way as well. Yep.
I did n over 10.
Beautiful. That was where I was going next. Why don't we just put n over 10? What's happening to the top? When I do the adjusted, it's adding 1 each time, so n is just changing by the size of an integer. But if you do it that way, where do you start? 4. Where do we end? 8. Perfect. So fine. Personally, I would have gone this second way as well. Much more compact, less complicated. Okay? So if you can do it that way, do it that way. If you can write it like that with a pattern on the bottom, meaning the 10 doesn't change, so I write it with a pattern on the bottom, I can do the same thing with a pattern on the top as well. Something that is consistent on the top. So I'm going to look at this one. The only adjustment that I'm going to make here is I'm going to rewrite this as 1 over 1. Okay? So I have 1 over 1 plus 1 over 4 plus 1 over 7 plus 1 over 10. There is one thing that is consistent in every single one of those terms, and that is 1 is on top. Now I'm going to look at the bottom. I'm going to separate the bottom from this. I just want to look at the series 1, 4, 7, 10, dot, 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 dot. The top is constant. It's always 1. The bottom is changing. Is the bottom changing in a pattern? Yeah. In fact, it's another arithmetic sequence, right? 1, 4, 7, 10, that's plus 3 every time. I have a D of 3. What's A sub 0?
0.
Negative 2, great. So my A sub n here is 3n, I want to make that minus, sorry, minus 2. 3n minus 2, that's what that says. And so that can be my denominator. Sometimes when you're trying to find the pattern, you may need to separate the top from the bottom to see if you can come up with a pattern, each of those individually. I need to figure out where I start and where I end here. Well, the ending's very easy. It's infinity. The start, because I chose to use the arithmetic form, the start will be at 1. I chose to write it as a sequence, to treat it as a sequence, even though they're separate from each other. The denominator is treated as a sequence. The numerator doesn't really matter. It's always 1 anyways. It's never going to change. So if I were to expand this, I'd have 1 over 3 times 1 minus 2, which is 1 over 1. 1 over 3 times 2 minus 2, which is 1 over 4. And it would continue out that way. So this is where I'd leave this guy. There are also going to be other occasions where the numerator and the denominator both change, but they change differently. So like this one where I separated the numerator and the denominator, on my next one, I'm going to do the same thing. I'm going to look at 2, 3, 4, and I'm going to look at 13, 17, 21, separate from each other. So when I set up my sigma notation, I'm going to have one formula that goes up on the top and another formula that goes on the bottom. And this isn't, every time I write an answer, there are infinite number of ways that you could write the same answer. So keep that in mind. I'm just going to try and do it so it's the most consistent. Both of these happen to be arithmetic again. And so I am going to use an arithmetic sequence to represent both of these. If I go back, I'm at 1. And so my a sub n for the numerator is 1n plus 1, or I can just write it as n plus 1. On the bottom, if I go back, I'm at 9. So my explicit form for that one is 4n plus 9, so I'll use that to represent the bottom. The key here is, when you separate them, you want to make sure that you can generate them the same way each time, so that I don't have to plug in something different for the top and the bottom, that every time the n that I plug in is going to get me the top and the bottom. And if I do it arithmetically or geometrically, I can always have that be ready, just because I'm going to force it to start at 1. I'm treating them like sequences, so they will always start at 1. That will give me the first term on the top and the first term on the bottom. And this one again is infinity. All right? This is the like a majority of the stuff that we're going to be working on. Just kind of putting it together, getting a feel, looking for if it's arithmetic. Is it geometric? Is it a special case? Is it a fraction that the top and the bottom act differently? Or is one consistent and the other one changes? But there is one other thing that you'll have to watch out for, and that we're going to finish on today. And that is sign changes. So alternating signs happen. And sometimes an alternating sign happens just because it's geometric and we're multiplying by a negative. But other times alternating signs happen and the pattern is not geometric. There's nothing I can multiply by 3 to get 5 and the same number to get 7 and the same number to get 9. In fact, if I look closely at the second one, it's an arithmetic pattern if I look at the absolute values. It's just that the sign is alternating. So let's go back up to, if it's geometric and it's an alternating sign, great, just treat it as geometric. This one is -3, comma 9, comma -27, comma 81, comma blah, 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 forever and ever and ever. And my a sub n is equal to the first number times what I'm multiplying by to the n minus 1 power. So my sigma notation is n equals 1, and this is going to infinity, and I take care of that again as a result of an alternating sign. Little side note on this guy. If a sub 1 matches r, just a side note, if a sub 1 equals r, you can cram this down into a more compact form. So I could write this as well as n equals 1 to infinity of -3 to the nth power. And that works because this would be -3 to the first times -3 to the n minus 1. Like bases, add your powers. That's -3 to the 1 plus n minus 1. The ones cancel out, leaving me with -3 to the n. Again, just a side note, that can happen, and you see that a lot. But back to what we were talking about. If it's alternating, if it's geometric, it's changing because r is less than 0. If it's not, I have to trick it into getting the right sign change. And so what I'm going to do is separate these values again. I'm going to look at 3 and 5 and 7 and 9 and 11, 13 and 15, and I'm going to try and find what's going on there. So I'm going to ignore the signs for a moment, take my brain off the signs. This is clearly an arithmetic, plus 2 every time. So my a sub n is 2n plus 1, because if I went back, I would be at 1. So when I set up my sigma notation, this is to infinity. I will start with 2n plus 1. I'm going to put it in parentheses because that's what's going to generate the number part of it. Now, what's going to generate the sign part of it? What do I multiply a positive number by in order to make it negative? -1. So great, -1. If I leave -1 there, what's going to happen in my sequence? Everything will be negative. I don't want that to happen. So I need to make sure that it alternates from positive to negative to positive to negative. And we do that with manipulating or by manipulating the powers. Remember, anytime I raise a negative number to an even power, it will become positive, right? If I raise a negative number to an odd power, it will stay negative. -1 squared is +1. -1 cubed is -1. I want to continue with that sort of pattern on my -1. I want the first one to be positive, which means that I need to put a power up here that is that is even. But the first thing that I'm going to plug in is 1. So that's not going to work. So I'll make it 2. Or if I wanted to, I could subtract 1 and make it 0. Does that make sense? Then when I plug in 2, to get my second term, I'll have a power of 3. That'll make the second term negative. When I plug in 3, I'll have an even term again. It'll make the third term positive. And it'll continue in that fashion. So that's how I fake my non-geometric series into alternating their signs. If it starts with a negative, I'm going to go through it the same way. It's just that my power is going to change a little bit. Okay, so there's nothing fancy there. I just have to make sure whatever I choose to put as the power on the -1 is going to generate the sequence or the series appropriately or accurately. So I'm going to start this again, 10, 20, 30, 40, 50. This one stops there. Again, plus 10. A sub 0 is 0. My arithmetic sequence explicit formula is 10n plus 0, or just 10n. So when I set up my series, I'll put 10n. Because I am treating it as a sequence, I'll start at 1 and I'll end at 5. And if I were to generate this right now, I would get 10 plus 20 plus 30 plus 40 plus 50. If I were to expand it out, but I want to have some alternating signs, so we'll introduce a -1. If I leave it at -1, they'll all be negative. I don't want that. I want it to alternate. So now I'm going to bring in a power. In this one, I want the odd powers, or I want every other one, the odd terms, 1 and 3 and 5, to be negative. So I can leave it at n. When I plug in 1, it'll be negative. When I plug in 2, for the second term, it'll be positive. When I plug in 3, it'll be negative. When I plug in 4, it'll be positive. Good? Are we okay with that? Okay. So again, when you're working with these, look for arithmetic first. Look for geometric second. Look for a special pattern, perfect square, perfect cube, factorial. If none of those exist, check to see if there's something else happening in numerator, denominator. Check to see if you can rewrite it so that it has a pattern. And make sure you're keeping it equivalent. And then lastly, watch for your alternating signs. So your homework is in your homework packet, and it is just a whole bunch of series. And you need to do them all for your assignment because it's excellent practice. So this is not an evens or odds day. There's no review on this. It's just a whole bunch of series that you want to write in Sigma notation. We have one section left.